What is going on, guys? Welcome back. In today's video, we're going to learn how to do professional benchmarking and how to plot professional benchmarking plots using PerfPlot in Python. So let us get right into it.
It's not a game, it's a rich thing.
Alright, so we're going to use PerfPlot to create professional benchmarking charts in today's video, and we're going to start with a simple example right away. But first of all, let us install the libraries that we're going to need in today's video. So we're going to open up the command line of our choice, and we're going to use pip to install, first of all, PerfPlot itself. And then in addition to that, we're going to need another library that you probably have installed already, namely NumPy. So pip install NumPy as well, even though I think NumPy is already a dependency here, so it should be installed automatically. But those are the two libraries that we're going to need in today's video. And then we're going to start with a very simple example. We're going to look at different ways in which we can concatenate two NumPy arrays. And then we're going to compare their performance depending on the input size. So we're going to say here import NumPy as NP, and we're going to say array 1 is equal to np random rand. We want to have 20 values here. We're going to copy that. Array 2 is the same thing. And then we're going to say here the first result that we want to have is np.c underscore, which is the concatenation operator or operation here. We say array 1, array 2. Then we also say result 2 equals np.stack. And we want to stack here array 1, array 2, and the result should then be transposed with a .t operation. Then we can do the same thing with a vstack. This is result 3. You don't need to understand, by the way, why all these are the same. This is not a NumPy tutorial. This is just a PerfPlot tutorial. We're going to use this here as an example. Res4 is np.columnStack. By the way, this is taken from the original documentation on the GitHub page, so this is actually the example that they use to show how PerfPlot works. Array 1, array 2, and then result 5 is np.concatenate, and this is a little bit tricky here. We need to say array, and then everything, none, array 2, everything, none, and then the axis is 1. So those are the 5 operations. And if we now look at res1, we can see it looks like that. If we look at res2, it looks the exact same way. Res3 looks the exact same way. So the result is actually the same. We can actually see that this is the case by printing np.array, what was it? Array equal res1, res2, and we can see that they're actually the same. We can now copy this and compare 2 and 3, 3 and 4, and 4 and 5. So of course this is a transitive relationship. If res1 and res2 are the same, and res2 and res3 are the same, res1 and res3 are also the same. So we can see all of those are the same, even though we use different functions. Now we are interested in which of those ways of doing things is more efficient? Which one should we use for different input sizes? And this is what we can find out with PerfPlot. So what we're going to do now is we're going to say import PerfPlot, and we're going to plot the performance depending on the input size. So we're going to say PerfPlot.show. We also can do, by the way, a .bench. The bench gives us a benchmarking table. The show gives us actually a plot, which is, in my opinion, more interesting. So we say perfplot.show, and in here we now add a bunch of keywords. First of all, the setup. So how do we generate the input data? The input data is going to be generated by np random.rand, as we did up here. Then the kernels are the actual methods. So the kernels are, in this case, we're going to pass this here as lambda expressions. We're going to say lambda a np. So we have one array np.c AA, then lambda a, and we do the same thing that we did above, basically. Here we take the same array with itself, but it doesn't really make a difference. .t, then we copy that. We have the vstack here, lambda a, np columnStack. By the way, if you don't know what lambda expressions are, I have a video on that, basically anonymous functions that we can write in a single line easily here. I recommend checking that out if you don't know what they are. And then the last one is np concatenate a none axis 1. So those are the different methods that we want to compare. Now let's add a bunch of labels here as well so that we know which one is which one. We're going to say this is C underscore, this is stack, this is V stack, this is column stack, and this is concat. I'm going to call it like that. And then we're going to say that the range, this is now the input range, how much do we want to have here as an input? We're going to say the n range is 2 to the power of k for k in range 15. So we grow this exponentially, and we want to compare the different sizes that we pass to the setup. And then we're going to say that the x label is the length of a. So that is that, and now we can run this here, and you can see that it's working. You can see that it makes progress for the individual kernels, and then in the end you can see also, not in the end, you can see also the overall progress. Once this overall progress reaches 100%, we can get the full graph. And since we're dealing here with actually significant sizes with 2 to the power of 15 or 14, this takes some time, but once this is done, you can see that for different sizes here. Now, actually, I'm not sure if this should happen because before I didn't see that. Maybe this was a problem in the execution. But essentially, you can see what happens. So you can see that some functions perform quite well with a small input size. So you can see here the concat function, so the concatenate function, is the best function to use when you have a small input size. However, over time, when we increase the input size, stack and VStack are actually better. So I think about running this again here because in my prepared code, I don't have such a spike. I think because essentially the y-axis is just the execution runtime. So if something happens, if my computer lags for a reason or something, for some reason, or something goes wrong, we will see that spike as well. I don't think that's because of the algorithm, so let's run this again and see if it appears again, because actually it's not about the VStack function. Now, as you can see, we don't have the spike. So you can see that with smaller input sizes, this purple line, the concat function, is actually the best one. But when we reached that input size here, VStack and stack are the better choices. C underscore seems always to be the worst choice, always takes the most time. But you can see how useful that can be here as a plot. We can also try to see what the bench function looks like, or the bench result. This is actually just a table. And then after that, we're going to look at another example, which is with Core Python, so not with NumPy. We're going to look at different methods to flatten a list of lists. So we have a list with multiple lists inside of that list, with elements in those lists, and then we want to have one flat list with all the elements. And there are many different ways to do that in Python. We're gonna see which one is the most effective. So here you can see with different ends what the execution times are. Can also be quite useful. Yeah, that is how you do that. So let's move on to the next one. Let's move on to the list in list examples, or sublist examples, flattening the sublist examples. Example, I'm gonna say here import functools. We're going to say import operator, which are core Python modules. And we're going to say that, for example, we have my values being equal to, I have a list here, 1, 2, 3. I have another list, 4, 5, 6. I have another list, 7, 8, 9. And those are part of another list, of a overall list, my values. And then we have different ways to flatten that list. So what we can do, for example, is we can say flat list equals, and we can say x for sublist in my values for x in sublist, and this will flatten the list. So if I now say flat list, you can see that we have just the values without the lists inside of the list. This is one way using a list comprehension. Another way would be to say flat list 2 is, for example, functools.reduce. This is a functional programming style of, or this is more the functional programming style here, but also the list comprehension already. We can say here the operator that we want to use is the concat operator. We want to apply it on my values. So now flat list 2 is also a flat list. So we have different methods. And what we're going to do now is we're going to write out all those methods and we're going to compare them. So most of them are going to be one-liners. We're going to start here with the list underscore comp. For the list comprehension, we're going to pass the values here, the list of lists with the values in there. And we're going to return exactly what we did above. We're going to say return x for sublist in values for x in sublist. That is one function. Another one is going to be the reduce method. Also takes values here, and then it returns functools dot reduce operator concat my values. Then def a sum method is also a method that we can use. So we can actually call the sum function on the values. When we pass here as a second parameter an empty list, this does the same thing. Then, by the way, if you don't believe me in any of those, just try them out. They all produce the same result. Then we can also use the numpy flat function, so values here as well. Here we essentially say, give me a list, but first of all, convert into a numpy array the values, flatten those values by using .flat, and return the list of that numpy array. So we typecast. Then we can also say numpy underscore concat. We can use a numpy concatenation from before. Return list np concatenate values. And then we can also say nested loops. This is probably a very inefficient way to do this, but we can say result equals an empty list here for sublist in values. What we want to do for x in that sublist, basically the list comprehension written out as a nested loop. Result dot append x, and then we return the result in the end. So those are the methods that we're going to use. Those are the functions that we're going to use. And now we can go ahead again and say perfplot dot show. And in here, we're going to say the setup is the following. We say lambda n, and we want to create a list of numbers. We want to create 10 values here. So the values 1 to 9, or yeah, 1 to 9, I think, or 0 to 9. I'm not sure. I think 0 to 9. And we want to take that list and repeat it m times, just so we see what happens with different input sizes. And then what we do is we say kernels equals, and now we just pass the functions. We don't even need lambda expressions because those are just the functions here. So we can say a list comp, we can say reduce method, we can say sum method, we can say numpy flat, we can say numpy concat, and we can say nested loops. And then we're going to say n range. So the input size is going to be 2 to the power of k for k in range 16. And we're going to say also again the labels are going to be list comp, reduce, sum, numpy flat, numpy concat, and nested loops. And then last but not least, the x label is going to be the input size, or the length of the list. So, okay, what do we have here? We forgot a comma. There you go. We have another problem. What's the problem? Operands could not be broadcast together with shapes 10, 9. Where do we have 10 and 9? What did I change that I did not have in my prepared code? So this happens, where exactly does this happen? Okay, do I have a problem in my code? We have concatenate values, we have array values flat. Okay, let me fix that here for a second. Okay, I figured out the mistake. The problem is that I use my values here and values here as a parameter, so this should actually be in the reduce method values instead of my values, because otherwise I choose the list up here. So we're gonna do that, and I'm gonna run this again, and you can see now that it's working. It's doing what it should do. And this basically now again runs with this input size. It basically creates the list of that structure with a different n. The n is determined by that n range function. So we pass that n range, whatever we get here in the iterations, to the setup to create the individual lists. And then we take those lists and feed them through the individual functions. The PerfPlot environment then waits and sees how long it takes, and then it plots the graph based on the results here. And in this case, we have, this takes more time because I think we're doing also larger input sizes. To the power of 15 is also part of the whole thing. And we have also different, we have also, I think, do we have more? We have 5 here. We have 6 functions here. So it takes some time, but in the end, we see then which of the functions perform the best. And the good thing about this is that we always see that different functions perform the best for different input sizes. So as we saw up here, we don't see it here in the graph now, but we saw that certain functions are better if we're dealing with small input sizes, and other functions are better when we get to really large input sizes. And we're going to see a same pattern here, a similar pattern here. I think now, there you go. You can see that if we want to flatten a list that is quite small, the sum or reduce function is actually the best way to go. Whereas the larger the input size gets, those are the worst methods. So you can see that this grows way faster. And if we have larger input sizes, we don't want to use reduce or sum because they are way slower than all the others. The best way to flatten a large list seems to be a list comprehension. So basically this way here. And also, not surprisingly, a nested loop that does the same thing basically as a list comprehension is always slower. This is something that we know. Those of you who have watched my Python Advanced, or was it Python Tips and Tricks tutorial series, know that list comprehensions outperform nested loops. And you can see that here as well. It doesn't even depend on the input size. You can see list comprehensions are always faster. Using NumPy is slower most of the time, as you can see here. I mean, for large input sizes, it's still faster than reduce or sum, but since we have to typecast and work with NumPy, obviously this is going to be slower. I think it would look differently if we have NumPy arrays and we have to flatten the NumPy arrays, and we could first typecast them into a list, then turn them back into a NumPy array. Maybe those would be then slower than the NumPy functions. But overall, you can see this is kind of interesting to see here as well. And you can play around with different examples. You can look up list functions or mathematical functions or algorithms. You can measure the performance and plot these professional benchmarking plots with PerfPlot. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and